This video was produced by the UCD Maths Support Centre in conjunction with the UCD Access Centre. The Leaving Certificate Maths paper has asked the definition of independent events before. Two events are independent if the outcome of one does not depend on the outcome of the other. Think about if one event is whether it will rain in your area and a second event is whether your local river will flood. The river flooding is dependent on whether it will rain or not. In contrast, an example of independent events is when the first event is whether a tossed coin will land on heads, and the second event is rolling a 6 on standard dice. There is no relationship between these events. The outcome of rolling a die does not affect the outcome of tossing a coin, and vice versa. If events are independent, the probability of the first event, event E occurring, and the probability of the second event, event F occurring, is equal to the probability of event E occurring multiplied by the probability event F has occurred. Or we can say the probability of E given that event F has occurred is equal to the probability of E. This means that even though F has occurred, it has no effect on the probability that E will occur. We can say this the other way around by saying the probability that event F will occur given that event E has occurred is equal to probability of F. The rule we're going to work with is this line here. This rule is known as the multiplication rule for independent events. We could also write this as the probability of E intersection F is equal to the probability of E multiplied by the probability of F. Our first question asks, what is the probability of a tossed coin landing on heads and a standard die landing on 6? So we are looking for the probability a coin lands on heads and the probability that a die lands on 6. This is equal to the probability from our multiplication rule of a coin landing on heads multiplied by the probability a die will land on 6. The probability a coin will land on heads is a half. The probability a die will land on 6 is 1/6. So multiplying that out, we get 1 over 2/6, which is 12. We have used the multiplication rule here because the events are independent. The next question asks us what is the probability of spinning the arrow in game A and it landing on 3 and spinning the arrow in game B and it landing on 2. The games are independent and all sectors are equally likely in the game. As the games are independent, we want the probability of one event and the probability of the second event. We can use the multiplication rule. We're going to apply this multiplication rule. So the probability that game A is equal to 3 and game B is equal to 2 is equal to the probability game A equals 3 multiplied by the probability game B equals 2. So looking at this first part, game A equal to 3. In game A, there are 4 sectors, so there are 4 possible outcomes, and only in one sector can the spinner land on 3. So the number of successful outcomes is 1, and there's 4 possible outcomes. So this probability is equal to a quarter. This is multiplied by the probability game B equals to 2. In game B, there are 6 sectors, and there are two sectors in which the spinner can land on 2. So the number of successful outcomes is 2 over the possible outcomes is 6. So a quarter multiplied by 2 6 is 2 over 24. Simplifying, we have a 12th. The last thing to state is that the multiplication rule can be applied to more than 2 events. For example, on screen you can see the multiplication rule for 3 independent events. The multiplication rule, also known as the AND rule, can be applied to n number of events. In this case, the probability of event 1 and the probability of event 2, 3, 4, 5, 6 and so on, all the way up to event n, where n is some number, is equal to the probability of 1 multiplied by probability 2 multiplied by probability of event 3 and all the way up to the probability of event n occurring. That concludes our discussion on the multiplication rule.